In this video we're going to talk about Unit 5, Objective 4, the limit definition of a derivative. So in order to show you the limit definition of a derivative, we're going to look at this graph here. You can see that it is ax to the fourth plus bx cubed plus cx squared plus dx plus e. The values of a, b, c, and d aren't really that important right now. What we're going to be looking at though is we have some point P that you can see on your graph. The x value we're just going to call x, and its y value is just going to be f of x. So when you plug f in, you get, or x in, you get f of x out. We're also going to have another point Q that has just moved off the screen, so let me move it in a little bit closer. So there's Q right on the right hand side. The distance between x, the x value of P, and the x value of Q is going to be some value h. So you can see if I move the point in a little bit closer, you can see that the x value of Q is x plus h. So the little distance in between them is h, and I can control how big h is by sliding it down here. So I'm going to move that back out this way a little bit for now. And then you can notice that the y value of Q is f of x plus h. So whatever x plus h is, we plug that into our function. That's going to be our y value. So our whole first big question of calculus was trying to find the slope of a curve at a point. So what we were trying to find was the slope of that tangent line right there. It's kind of cut off, but it's saying it's 0.45. I can move that in a little bit so you can kind of see it a little bit better. The slope's 0.45. So what we tried to do at the beginning, before we knew how to take a derivative, is we made a secant line. And I can move this in a little bit so we can see that slope's a little bit better. And we would use that to estimate the slope of the tangent line. But now that we have limits, we can make a better estimation of that tangent line. So if we think about the slope of that secant line, the slope of that secant line would just be the y value f of x plus h minus the y value f of x, so y minus y over your x values, so we have x plus h minus the other x value x. So that's going to simplify to give us f of x plus h minus f of x over h. That's the slope of our secant line PQ. So what we can do to try to better estimate the slope of the tangent line is we can make h a little bit smaller. I can move those points closer and closer and closer. And as we can see, the slope of the green secant line is getting closer to the slope of that black tangent line. So all we have to do is decrease the length of h. So eventually we can put them right on top of each other, and the slopes are going to end up being the same thing if that distance between x and x plus h is 0. So we move this a little bit so we can see it a little bit better. So if we move them so the x plus h and x are the same point, we're going to have the same secant line equaling the tangent line. So if h is 0, we're actually going to be looking at f of x minus f of x over 0. So that really doesn't help us. We can't find that numerically. But what we can do is we can take a limit of that difference quotient that we had, and that's going to be a derivative. And it looks like part of that fell off, so we can kind of add this in here. The limit as h goes to 0. So if we are thinking about what we just said, we have the difference quotient, the old slope formula, f of x plus h minus f of x over h. And that h was the distance between the point of tangency and the other point on our secant line. If we make that distance between those 2 points 0, we're going to find the slope of the tangent line. So that's where our derivative definition comes from. The limit as h approaches 0 of f of x plus h minus f of x over h. So we'll write that on this screen so it's a little bit easier to see. So we can say f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. Now, how this is more than likely going to show up on AP is they're not going to mention derivatives at all. They'll probably give you a problem that would look like this. So the limit as x, I'm sorry, not x, but h approaches 0. Get rid of that x. The limit as h approaches 0 of x plus h cubed minus x to the third over h. Now, if we think about just plain old limits for a second, we would start this problem by trying to substitute 0 in for h. That would give me x plus 0 is x to the third power minus x to the third power is 0 over 0. So we'd get a situation where we have 0 over 0, and we can use L'Hopital's rule. So we could answer this without using our limit definition of a derivative. But they can ask this in such ways where you have to understand it's a derivative. But if we go back to our limit definition, we have f of x plus h, which means I plug x plus h in for my variable, minus f of x. So if we look, f of x could be x to the third, which means if I plug x plus h in, I would get x plus h to the third. The giveaway that this is a derivative problem is this h goes to 0 right here, because our limit definition says h goes to 0. So if we can recognize that this is actually a derivative problem and that f of x is equal to x to the third, we know this is asking for f prime of x, which is just going to be 3x squared, and we don't have to go through the L'Hopital's rule process. There's one other definition for a derivative using limits, and that's for the derivative at a point. And that limit definition says this: the limit as x approaches a, and a is just some constant, of f of x minus f of a over x minus a. So how this might show up is something that looks like this: the limit as x approaches 3 of the square root of x plus 1 minus the square root of 4 all over x minus 3. So on this one, the giveaway that this is a derivative, actually we'll go ahead up here and we'll say that this is equal to f prime of a. So take the derivative and plug a in. The giveaway that this is the derivative problem is we have f of x over x, we have f of a over a. So we're subtracting the same thing in the top and the bottom. It's our f values, our y values over our x values. So it's like the old slope formula. So what this question down here is really asking for is f prime of 3. So in order to find f prime of 3, we need to think about what is f of x. If we look at our definition, f of x comes first, f of a comes second. So if we're thinking about it that way, f of x could be the square root of x plus 1. And if you want to check it, our f of 3 should be the square root of 4. And if we plug 3 into the f of x that we just said, we do get the square root of 4. So we do know that this right here is going to be our f of x. So now we just take our derivative. So f prime of x is going to be equal to 1/2 x plus 1 to the negative 1/2 power using our chain rule. The problem wants f prime of 3. So we get 1/2 times 4 to the negative 1/2 power, which is 1/2 times 1 over the square root of 4, which is going to give us 1/4. So the trick to these is we need to have the two definitions of derivative memorized, because AP can ask these questions in such a way that you can't use L'Hopital's rule. If you check, you can use L'Hopital's rule for this question the way it's written, but they can ask questions that make you understand that that is the limit definition of a derivative. So we need to know both limit definitions and know how to find f of x from those limit definitions. So that's going to do it for this video. We'll see you in the next one.